Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good morning. Salam sejahtera to all the students. Okay, I will continue with chapter 8, Quantization of light. Just to recall back or overview about the topic of 8, Quantization of light, where you have two subtopics. First one is Planck's quantum theory, and 8.2 is about photoelectric effect. Planck quantum theory has been covered by Puan Almadia, and my turn is to cover photoelectric effect. So we will explore more about photoelectric effect and then go to the Einstein photoelectric equation for problem solving. So the photoelectric effect subtopic 8.2. Okay, what are the objectives for subtopic 8.2? The first one is define photoelectric effect, and then explain the phenomena of photoelectric effect by sketching the diagram of photoelectric effect experimental setup, and define threshold frequency, work function, and stopping potential. So you have a few terms here. And then explain the failure of classical theory to justify the photoelectric effect. And then a few more objectives. Analyze by using graph and equation the observation of photoelectric effect experiment in terms of the dependence of first one, kinetic energy of photoelectron on the frequency of light, where you have this equation. We'll go into this one later. And then photoelectric current on intensity of incident light. And the third one is work function and threshold frequency on types of surface, whereby work function equal to hf0. Threshold frequency times the Planck constant equal to the work function. And we use Einstein photoelectric equation for kinetic energy maximum. K maximum stands for kinetic energy maximum. So it's equal to energy of electron volt E times the stopping potential, or equal to Hf minus W0. So what is photoelectric effect? Okay, you have learned about this the previous lecture. So just to recall back, photoelectric effect, okay, when you have the photon energy or the light striking a metallic surface here, any metal surface, and then all the photon energy transfer to the electron inside the metal, where you have the free electron inside the metal, and then electron will be emitted and escape from the surface of the metal. The energized electron can overcome the attraction for the nucleus and escape from the surface. But an electron can escape only if the photon provide enough energy. Proton provide enough energy, that is the energy for the work function. The energy from the photon should be more than the needed energy to eject the electron. That is referred to the work function of the metal. This experimental setup, okay, you have gone through about this also, where you have the evacuated glass or quartz tube, then you have the collector and emitter. Emitter is when you have that is the metal target, and then incident light shine into the emitter, and then electron will be ejected from the metal target. Here is we call collector. Collector is connected to the positive terminal. How we know that there is a current flow? So the emitter is here to detect the current. So you have the emitter to know whether the current or the electron flow through the circuit. Here the animation. Okay, you have the striking the metal target, and then here you have the gap. After the electron emitted from the metal target and close the gap, move through the circuit here, and then you can see the emitter show the reading, meaning that there is a current flow. That is photoelectric effect. Photo stand for the word photo refer to light, and electric refer to electron. So when light shine on the metal target, photoelectron will be emitted and complete the circuit, and you have the current. Similar thing just now as previous slide. Okay, observation from the photoelectric effect experiment. When the apparatus is kept in dark, meaning that there is no light, emitter reads 0, indicating no current. So no light, no current. When plate E, emitter is illuminated by light having an appropriate frequency. And the word here is appropriate frequency. Current is detected by emitter, indicating there is a flow of charge across the gap between the plate E and C. When the potential difference is increased, more photoelectrons reach the collector, thus the photoelectric current increase. Positive voltage becomes sufficiently large, the photoelectric current reach a maximum constant value, which is called as saturation current. So it is the maximum constant value of photocurrent when all the photoelectrons have reached the collector. If the positive voltage is gradually decreased, it decreases the positive voltage, the photoelectric current I also decrease slowly. Even at 0 voltage, there are still some photoelectrons with sufficient energy reach the collector. Finally, when the voltage is made negative, that is the reverse voltage. Voltage is made negative by reversing the power supply terminal. You reverse the terminal of the power supply, then the photoelectric current decrease even further to very low values, since most photoelectrons are repelled by collector, which is now negative electric potential, which we call stopping potential. Okay, we go to the Einstein Equation for photoelectric effect. Einstein Equation here for problem solving. Okay, a few terms that you need to know to solve the problem. The light with frequency F that incident on the emitter or metal target can be regarded as collection of discrete packet of energy called photon. Quantum theory, Planck's quantum theory said light can be considered as collection of discrete packet of energy called photon. Particle properties of light we call photon. And each packet contains an energy E equal to h times F. Planck constant times the frequency of the light, or when you have the wavelength, you can use equation E equal to hc over lambda. Okay, Planck constant 6.63 times 10 exponent negative 34. The unit is joule per second. F is the frequency of the light, and c is the speed of light in vacuum. Constant value, which is 3 times 10 exponent 8 meter per second. Then lambda is the wavelength of the light. So when you use this equation, E equal to hf or E equal to hc over lambda, the units here is joule, because h is joule per second. Unit for the energy is joule. Okay, about Einstein equation just now, the interaction of light and matter at the atomic level involve an atom absorbing a single quantum of light. It cannot be subdivided. The energy will be given up to an electron in the metal. Okay, light shining on the metal, and then the energy will be given up to an electron. So specific amount of energy W0 is required for an electron to leave its atom and be ejected from the surface. The energy or work required to move the electron depends how strongly the electron is held. So when light shine on the metal target, okay, the energy should be given to the work function first before we can have the kinetic energy maximum. If the photon energy is greater than the required energy to eject the electron, then the excess appears as kinetic energy of the ejected electron. So energy will be given to work function first. Then the balance or the remaining energy will be given to the kinetic energy. So to summarize the Einstein equation for photoelectric effect, it is basically the conservation of energy. So energy in equal to energy out, or energy before equal to energy after. Energy before come from the photon energy. Photon energy, how to calculate photon energy? Equation just now, HF or HC over lambda. And then work function, W not stand for the minimum work to eject an electron, minimum energy to eject an electron. So it depends on the type of metal, and after that the remaining of the energy will go to the kinetic energy maximum of the photoelectron. So you have the term work function, W naught refer to work function, and it depends on the type of the metal. So definition of work function. Work function is the minimum amount of energy required to remove an electron from a metallic surface. Okay, here you have a table for 5 elements here: aluminium, sodium, copper, gold and silver. So this element or this metal have its own work function. For example, aluminium has 4.3 electron volt work function, sodium just 2.3 electron volt work function, copper higher from sodium 4.7 electron volt, and then you have gold and silver. So it is constant for the specific metal. Okay, let's say here you have the metal, your metal target is potassium, so it needs 2.0 electron volt to eject an electron, meaning that 2.0 electron volt is its work function. Okay, let's say the light that shine on the potassium metal is 1.77 electron volt. That is the energy. We have energy in units of joule and also electron volt. So 1.77 electron volt from the photon. And then we shine on the metal target here, which is potassium. No photoelectron emitted, or no electron emitted, no current if you have the photoelectric effect experiment set up. And then you change you change the color of the light, you change the wavelength of the light, or the frequency of the light. Let's say here we have 550 nanometer of light. The energy, okay, calculation of energy of the photon equal to Hc over lambda. You will get 2.25 electron volt. And then check work function of the potassium is just 2 electron volt. So meaning that 2.25 minus the work function 2.0 volt. So the potassium need the minimum energy of 2 electron volt, but then from the light, the photon energy give 2.25 electron volt, more than needed by the potassium metal target, and then that's why the electron can be ejected from the metal target, and then it has the balance of kinetic energy. 2.25 minus 2.0 electron volt, the other 0.25 electron volt giving to the kinetic energy of the ejected electron. Then when you calculate the velocity of the ejected electron, you get 2.96 times 10 exponent 5 meter per second by using equation of kinetic energy half mv square. Okay, let's say you have the wavelength of the light is 400 nanometer. Just now is 550 nanometer higher, and then this is lower from the green light here. So the energy from the photon is 3.1 electron volt. Potassium needs work function of potassium is just 2 electron volt. Then the excess of energy is 1.1 electron volt. So the ejected electron will have more energy for its kinetics energy, and then its speed also higher compared to just now when the photon energy has the wavelength of 550 nanometer. If photon inversely proportional to its wavelength. Wavelength higher, lower energy. Lower wavelength, higher energy. For the frequency, it is proportional to the frequency. Higher frequency, higher energy of the photon. And then the term threshold frequency, or called as cut-off frequency, we label it as F0. So F0 is the cut-off frequency, which is the minimum frequency needed to eject an electron. The minimum energy, the minimum frequency needed, not the minimum, okay, the minimum frequency needed to eject an electron. So based on this metal target, what is the minimum frequency needed just to eject an electron? So work function W0 equal to HF0, and then when you use the wavelength, so it's equal to Hc over lambda 0. The frequency here refer to the incoming light. Incoming light has given enough energy for the work function. Kinetic energy maximum. Okay, the next one is kinetic energy maximum, where you have Einstein equation equal to work function plus kinetic energy maximum. So you just rearrange the equation. Kinetic energy maximum equal to, this is photon energy H times F minus the work function. So electrons are given off from which a range of kinetic energy from 0 to maximum. So the electron that are ejected from the metal has velocity from 0 to maximum value. So it depends on the incoming light, which is the photon energy, and the work function of the metal. Okay, let's see here, when you have HF or energy from the photon more than the needed energy to remove or to eject the electron from the metal, so the frequency of the light is more than the frequency of the metal target to eject the electron, then you have the kinetic energy. Electron is ejected and it has its speed. K maximum. Electron is emitted with maximum kinetic energy. So it has balance of the energy from work function given to the kinetic energy. Okay, look for the second case. HF equal to W0, or the frequency from incoming photon equal to the minimum frequency needed to eject the electron. So what happened here? Okay, when HF equal to W0, okay, the metal can be ejected from the metal target, but then no energy for the kinetic energy. That's why V equal to 0. Just to eject the electron from the metal. When HF equal to W0, no more energy for the kinetic energy. So K maximum here equal to 0, because all the energy go to the work function. Electron is emitted, but maximum kinetic energy is 0. Third case, when the if photon energy from the light less than work function, not enough energy to kick the electron from the metal. So there is no photoelectric effect can be observed. F less than F0. So nothing happened. No electron is emitted. So how to calculate or how to determine maximum kinetic energy and stopping potential? Actually, maximum kinetic energy relates to stopping potential. So maximum kinetic energy can be determined from the stopping potential. Stopping potential is defined as the reverse potential difference. You switch the potential difference required to stop the fastest ejected electron from reaching the collector plate or give zero current. When the emitter indicates zero current, so give zero current here. Okay, how to determine stopping potential? Okay, here is the normal case where you increase the voltage and get the maximum current, and then to determine the reverse stopping potential or reverse potential, Vs. Okay, we reverse the terminal of the battery. Positive here will become the negative, and that is connected to the negative terminal of the battery. Reverse the polarity. So electron emitted from the metal target will be repelled by the negative electrode. The reverse voltage is increased until galvanometer detect no current. Galvanometer or emitter detect no current, meaning that no electron have sufficient kinetic energy to reach a collector. No more electron can reach the collector. So the voltage here is called potential or stopping voltage. So we can measure the stopping voltage. Okay, take a rest and quick check for this question. What you have learned from the slide I shown you just now. Okay, the work function of metal A is 3 electron volt. Metal B and C have work function of 4 electron volt and 5 electron volt respectively. Ultraviolet light shine on all 3 metals, creating photoelectrons, meaning that electrons are emitted. So rank in order from largest to smallest the stopping potential for A, B and C. Okay, you have 3 metal here. A work function 3, and then B work function 4 electron volt, and work function for C is 5 electron volt. And then the same photon energy shine on these 3 metal. We need to rank in order from largest to smallest the stopping potential for A, B and C. Okay, recall that when light shine on the metal target, the first thing is give to the work function. And then the balance goes to the kinetic energy. Metal C has 5 electron volt work function, so it has the higher work function. Same energy from the photons, so meaning that when it has the metal C has highest work function, so less energy can be given to the kinetic energy maximum. So the stopping potential for A, B and C, VA has higher stopping potential because its work function it has the least work function, just 3 electron volt, compared to B 4 electron volt and 5 electron volt for C. So the answer for this question is VA should has more stopping potential for A more than stopping potential for B, and then stopping potential of B more than stopping potential of C. C has the highest work function, so less energy given to kinetic energy maximum. Kinetic energy maximum relates to stopping potential. The highest kinetic energy maximum, the higher its stopping potential. So we continue with the graph of photoelectric effect experiment. Just now is problem solving. using Einstein Equation. And then this is the objective about sketching the graph. So the first graph is how the intensity of radiation affects the photoelectric current. Meaning that you change the intensity of radiation. What happened to your photoelectric effect experiment? What are the observations that you can see? A light with frequency that can eject electron is incident on the metal plate. In order to see the the current or the electron emitted from the metal plate, the frequency should be more than the needed energy for the work function. Potential difference is increased and then reverse the polarity. Reverse the polarity to determine the kinetic energy. Then you recorded the current. After that, the experiment is repeated using radiation of various intensity but keeping the frequency constant. So frequency is constant, but then you increase or decrease the intensity of the light. Okay, the result or the observation when the intensity change. Okay, first one is intensity, this one. Okay, the stopping potential here, okay, when you have the higher intensity ini sekali saja, ni 2 kali, so that you can see your x-axis V, potential. V as refer to the stopping potential. Stopping potential do not change here, it's still at the same point. But then the maximum current increase, and you have twice intensity of the light. So the current increase as the potential difference increase, but finally come to maximum value. This is because all the electrons are collected at sea and the current cannot increase further. Still you have the graph of current against voltage, and then it's come to the maximum current. And then when you higher the intensity, then the maximum current becomes higher also. Current finally comes to 0 at the stopping potential here. So stopping potential, current is 0, y-axis is 0. Current maximum is found to be proportional to the intensity of the light. Higher intensity, higher maximum current. No matter how large is the intensity, the stopping potential remains. Okay, intensity here refers to more photon per second coming to the metal target. For the radiation of different frequency, okay, let's say you have radiation or incoming photon from different frequency, but then using the same metal and intensity is fixed. Okay, when you fix the intensity, meaning that the saturated current or the maximum current still at the same point here. Okay, different frequency. Different frequency means that different energy of photon. Higher frequency have higher energy. Okay, here you have same metal, but then different frequency of energy from the radiation. That's why you have 2 points for the stopping potential. F2 more than F1 here, because when higher frequency coming to the metal target, so it gives more energy to the metal target. After minus the work function, then it has more kinetic energy. More kinetic energy, higher stopping potential. So V2 more than V1, and don't look at the negative point here. The stopping potential is just you take the value, not the negative sign here. Let's say this is negative 5, then the stopping potential is 5 volt, not negative 5 volt. So here let's say this Vs1 is negative 5, Vs2 is negative 10. Actually, Vs2 is more higher compared to Vs1. 10 compared to 5, not negative 10 compared to negative 5. This is the reverse potential. Okay, then you change different metal, but the intensity and frequency of the radiation are fixed. Intensity fixed, meaning that maximum current fixed is at the same point here. Frequency fixed, energy of the frequency refer to energy of the incoming photon, so fix the energy from the photon, but then two different metal means that two different work function. Okay, let's say work function of metal 2 is higher than work function of metal 1. So your graph, okay, this one is for the metal 2 and then this one is for metal 1. Since work function of metal 2 more than work function of metal 1 and energy from the photon is the same, so more energy is needed for the metal 2 in order to eject the electron. So the remaining kinetic energy less compared to the metal 1. That's why stopping potential of metal 2 is lower than stopping potential of metal 1. They shift, okay, metal 1 dia ada higher potential, they shift to the left, higher voltage. Then the dependence of kinetic energy on the frequency of light. Kinetic energy, okay, when you reverse the potential, reverse potential is applied to the emitter or the metal target and increase until the emitter reading is 0. The photoelectron with maximum kinetic energy are stopped. The experiment is repeated. Okay, we repeat the experiment with different light. Then we need to sketch the graph of kinetic energy against frequency. Okay, frequency x-axis and then y-axis is kinetic energy. Here is we can measure the stopping potential. So in terms of the energy, stopping potential times 1.6 exponent negative 19, you get the energy. So when you plot the graph, you get the linear graph. Equation y equal to mx plus c, based on Einstein Equation. Hf equal to EVS is kinetic energy maximum plus the work function. Okay, your y-axis is K maximum, K maximum, and then work function. Okay, work function is the intersection of the y-axis. So what you can get from the graph of K maximums against the frequency, x-intercept is equal to the cut-off frequency. Cut-off frequency here, okay, kinetic energy maximum equal to 0. Then the frequency here refer to the cut-off frequency to eject the electron. The minimum frequency from the photon, from the radiation needed to eject the electron. Y-intercept is equal to the work function. Equation K equal to Hf minus W naught. So intercept at negative value here. And the slope of the line is equal to Planck's constant. Vs equal to 0. This point Vs equal to 0. So K maximum equal to 0. X-intercept will give you the cut-off frequency. And when you have a graph of K maximum against frequency, how to get the threshold frequency? Just refer to the X-intercept. Okay, let's say we have different metal. Still the graph of kinetic energy against the frequency. We have metal 1, metal 2 and metal 3. Then it has different threshold frequency based on its work function. Given here work function metal 3 more than work function metal 2 and more work function metal 2 more than work function metal 1. So when you sketch the graph, to the right should be metal number 3. Metal number 3, it has the highest work function. So when it has the highest work function, its cut-off frequency also the highest. Work function 3 more than work function 2. So frequency of threshold frequency of metal 2 less than frequency of threshold frequency of metal 3. Equation of work function equal to HF0. Higher work function, higher threshold frequency, proportional to, and work function proportional to threshold frequency, threshold of cut-off frequency. And then next concept, okay, quick check whether you understand or not. The intensity of a beam of light is increased, but the light's frequency is unchanged. Okay, you change the frequency, keeping the frequency constant. Which of the following is true? Okay, A, the photons are larger. B, there are more photons per second. C, the photons travel faster. D, each photon has more energy. As I said just now, intensity refer to more photon coming to the metal per second. So the correct answer here should be B. And the photon cannot be larger or smaller. The photon cannot be travel faster or lower because the proton travel at speed of light, constant speed. Each photon has more energy. If photon of the same frequency, the energy are equal. So the correct answer should be B. Then the final objective is to explain the failure of wave theory of light to justify the photoelectric effect. Wave theory is what you have learned in semester 1. Photoelectric effect is a proof that light behaves as particle, quantum theory. So we compare wave theory with quantum theory. In principle, there is no conflict between the wave model of light and observation of photoelectric effects. Work must be done or energy is used to remove the electron from the metal. A wave is a means of transferring energy from one point to another. This is what you have learned in semester 1. Thus, when the light wave is incident on the metal, it transfers the energy to the electron as it passes over them. But there is a difficulty in explaining the properties of photoelectric effect by the wave model. That we say the failure of wave theory to justify the photoelectric effect what have been observed during photoelectric effect. Okay, in terms of photoelectric kinetic energy versus light intensity. Okay, wave theory said that electron absorb energy continuously from the light. So as the light intensity increase, larger amplitude. So intensity of the wave is proportional to the amplitude squared, semester 1. So energy should be transferred into the metal at higher rate and the electron should have more kinetic energy. That is wave theory. For the photon theory, light of greater intensity means that more photon coming per unit time to the metal surface. So the number of electrons ejected per second increase. One photon gives to one electron. When you have so many photons, then so many electrons can be ejected per second. So the current will increase when more electron flow. However, the photon energy remains. Remember that photon energy is equal to HF, Planck's constant times the frequency of the light. So the maximum kinetic energy does not depend on the number of photons inside the metal surface per second, because each emitted electron is a result of the absorption of one photon. So in terms of energy, for the intensity of the light, it doesn't count for the energy. When you have more intensity, the energy still remains. And then dependence of photoelectron kinetic energy on light frequency. When you decrease or increase the light frequency, wave theory said there should be no relationship between the frequency of light and the electron kinetic energy. The kinetic energy should be related to the intensity of the light just now. Wave theory said kinetic energy should be related to the intensity of the light, meaning that higher intensity, higher kinetic energy. But then for photon theory, the maximum kinetic energy of the photoelectron increase with increasing light frequency only, not depends on the intensity. No matter how small the intensity of the light, it still can give the energy to the metal target. So Einstein Equation Ke maximum equal to Hf minus W naught. If the photon energy more than work function, then there will be energy for the kinetic energy. In terms of threshold frequency, wave theory said the photoelectron can be emitted at any frequency as long as the light intensity is high enough. There is no threshold frequency. So for wave theory, there is no threshold frequency. But for photon theory, no photoelectron are emitted if the frequency of the incident light is less than the threshold frequency. Photon must have energy greater than the work function in order to eject an electron. If energy of the incoming photon does not satisfy this requirement, then the electron cannot be ejected regardless of the light intensity. So photon theory said it not depends on the intensity again for the threshold frequency. Instantaneous emission of photoelectron. Wave theory said electron needs time to absorb sufficient energy to escape. There will be a time lapse before photoelectrons are emitted. An electron must gather sufficient energy before emission, hence there is a time interval. The words here is time interval. Wave theory said there is time interval between absorption of light energy and emission of the photoelectron. Time interval increase if the light intensity is low, needed more time. Photon theory, when radiation of frequency more than threshold frequency, photoelectrons are emitted instantaneously. How lower the intensity, no matter how lower the intensity, as long as the frequency of the light more than the threshold frequency, then photoelectrons are emitted instantaneously. Okay, for attendance purpose, please scan this QR code. So make sure attendance is taken. So thank you. That's all for lecture of 8.2. Thank you for watching. Assalamualaikum warahmatullahi wabarakatuh.